Doc, I think it is time we can start now.
Okay, I'm set.
Yes, sir.
Good morning, everyone here present.
Good
Uh,
morning, sir.
okay, we are about starting the third lecture of this forum. If you could remember, for those that are joining for the first time, we started this thing exactly 2 weeks ago. The moment we stopped addressing the questions, the speaker, which is Dr. A.T. Imam, will respond to the questions, after which will not accept any questions. Will not accept any question. Thank you and good morning. Over to you, Dr. A.T. Imam. You have the floor.
Thank you very much, the chairman. Um, we are all welcome to
A.T.
the
Imam,
third. Thank you very much, sir. Can you hear me, sir?
you have
Okay.
the floor.
Thank you very much, Mr. Chairman. Can you hear me now?
Hearing you clearly.
Okay, thank you very much. You are all welcome to our third lecture. This is the lecture where we are going to cover monogenic semigroup, ordered sets, and semilattices. So, as we have mentioned earlier, the lecture is going to be based on the book Fundamentals of Semigroup Theory by John M. Howie. So, as I have said, in this lecture, we are going to cover about three topics: monogenic semigroups, ordered sets, and semilattices. So, we start with the notion of monogenic semigroup. We consider an index family, UI, of sub-semigroup of a semigroup S. It is an easy exercise to see that the intersection of any family of sub-semigroup, if not empty, it is again a sub-semigroup of S. If not empty here, because in group theory, whenever you take intersection, the intersection is always not empty, due to the fact that the each of these subgroup will contain identity element. So at least always identity element will always be a common element. But in semi-group theory, a semi-group doesn't necessarily have to contain an identity element. And so therefore, uh, the intersection of a given family may be empty. So, but whenever it is not empty, it is again a sub-semigroup of S. And so, uh, one can talk of giving a subset for any non-empty subset A of a semigroup S. The subset A not necessarily a sub-semigroup. One can speak of the semigroup or sub-semigroup containing A. In fact, there is always a sub-semigroup containing A, uh, namely S itself is always a sub-semigroup containing A. So one can
Which of these
consider.
elements are generators? That is, you find the order of each element in Roman 1 and 2. Some are generators,
Please,
some are not generators. Which
Mujita,
among them are generators?
Mujitaba, please, off your
Sorry,
mic. We are recording.
is he asking a question
Mujitaba,
or what?
Mujitaba, what? Use this Mujitaba?
Let me check.
Who's that Mujitaba? Mute your Mujitaba. I don't know who could that be.
Mujitawawa. Okay, I think it's all right. He has been muted, sir. I'm talking about if considering if an index family of a sub-semi group, the intersection of the family uh, is always a sub-semi group whenever it is not empty. I was trying to explain the fact that an intersection of a sub-semi group, if you take, even if it is just two sub-semi group in a semi group, the intersection may be empty. So whenever the intersection is not empty, then the intersection is always again a sub-semi group. This is a simple fact that can be proven, because if you take any two members of the intersection, the product will still be in the intersection, given the fact that the members of the family is a sub-semi group. So if that is so, one can look at a situation where you pick a non-empty subset. So if you pick a non-empty subset and you consider an entire family of sub-semi group containing A, that is a family of sub-semi group where each and every member of the family has this element, this subset A inside it as as a subset, then that family, if you take the intersection, it will always be a sub-semi group. So the intersection of a family of sub-semi group containing A is the one we denote by A with angle brackets. And that is defined to be the intersection of all sub-semi group of S, such that A is contained in the sub-semi group. This is the one that we refer to as the sub-semi group generated by A. Sub-semi group generated by A. Actually, this sub-semi group is defined by two properties. By virtue of its definition, you can see that it is the intersection of all sub-semi group containing A. It means it too contains A. So the intersection of all sub-semi group containing A will also contain A. And if U is any other sub-semi group of S containing A, then the intersection will be contained in it, meaning this intersection of sub-semi group containing A is the smallest sub-semi group of the semigroup S containing A. And so therefore, these are the properties. It is the smallest sub-semi group containing A. And it will be also easy to see that in lemma 1 here, we present that this sub-semi group consists of all elements of S that can be expressed as a finite product of element in A. So because if you go by the definition here, you see, if one give you a subset A and say, what is the sub-semi group generated by A? It means you have to form the intersection of all the sub-semi group containing A. But this intersection, you may not be able to get hold of all the sub-semi group of S containing A, because there may be too many of them. There may be too much. It depends on the size of the semi group, and when you are talking about sub-semi group, it can be any large number. So you may not be able to get hold of the all the sub-semi group containing A. So in other words, this definition may not be practically used in trying to uh, get this sub-semi group generated by A. And so therefore, this lemma is telling us that the precisely this sub-semi group generated by A, or the intersection of all sub-semi group containing A, consists precisely of element of S that can be expressed as a finite product of element in A. Meaning, if I pick any element from here I will see that it is just a product of members from A. And to see this, if you let A bar to be the set of all finite products of elements coming from A, AI is coming from A, then clearly A will be contained in A bar, because this will is obviously a semigroup, is a sub-semigroup of S. And if you take one product, so this obviously contain A, and so therefore uh, A is there, and it is a sub-semigroup. So therefore, the smallest sub-semigroup contained in A will be in it. And then the other inclusion is also clear, because if you look at all members here, the products are from A, and this semigroup here contain A, so, and it is a sub-semigroup, so products of elements coming from A will be contained inside here. So this is not difficult to see that the smallest sub-semigroup contained in A will be the same thing as the uh, product, the semigroup containing all finite products of element in A. So this is how we describe the sub-semi group generated by A. So if it happens that when you generate a sub-semi group by a subset A, and the result of the generation is equal to the entire semigroup, then we say that A is a generating or is a set of generators, or is a generating set for the semigroup. So this is how we define a generating set. And then we will see later many examples of this notion, actually, where we look at the full transformation semigroup and we try to generate using idempotent or quasi-idempotent many special type of element. So, and the advantage of obtaining a generating set in semigroup theory here is to actually, it's just like the same type of advantage of getting, yeah, the rank. Actually, it is always true that in most of the situation that the generating set is smaller in size than the entire semigroup. And so if you can get hold of the generating set, you can achieve studying the semigroup, even though it is large, via studying the smaller set A, which contain fewer elements. And that is, and with the hope that you can extract some information about the semigroup via studying corresponding information in the generating sets. And this aspect of generation is just like the notion of linear span in vector space. And when we talk of the smallest size of a generating set, that is also the corresponding notion of dimension in the setting of vector spaces. And so if A is finite, then we shall use the notation A1, A2, A3. Rather than writing the set inside the brackets, we just write, list out the elements separated by comma, to pronounce the sub-semi group generated by the finite set of element A1, A2, An. And in the special situation where A is just a singleton, we write the sub-semi group generated by this a one single element to be equal to this. You remember by the lemma here, lemma 1, that sub-semi group generated by the collection of element A consists of all elements that can be expressed as finite products of element in A. So if you are talking about one single generator, it means all elements that can be written as product of just one element A. And this will be all powers of that element, A square, A cube, A4, up to infinity. Actually, and this may be infinite and it may be finite, because the sequence may terminate and start repeating, or it can continue infinitely many times like that. Now, if S is a monoid, then we can equally talk of the submonoid of S generated by A. So if there is an identity here and you are talking about submonoid, even the sub-semigroup generated by A should contain the identity. So which means in taking the powers or in multiplying, you have to use a power where the index is 0 there. So in that case, you must to impose the condition that identity must be there. So the numbers here in this lemma here, it means here you will not work only with the natural numbers. You have to include 0 in the set of the natural number, so that a certain power or a certain product of the element of A should be equal to 1 in that case. So one can decide to say, if the semigroup is a monoid, then you are looking for the submonoid. But if you are looking for only subsemigroup of the monoid, then you don't have to include powers with index 0. And in the special case where we have a single element that is just a subsemigroup generated by one single element, we start counting the members from 1. So we start by saying a to power 0, a to power 1, a square, and so on, to ensure that 1 is always there, because we are talking about the subsemigroup, submonoid generated by a single element. And then here we define what we call monogenic subsemigroup. Monogenic subsemigroup is just referring to the subsemigroup generated by a single element. Just like in group theory, this type of subgroup is called cyclic subgroup instead of monogenic. But we use the term monogenic. Here we'll see why we are saying monogenic and not cyclic in a very soon we'll see that. So we refer to the subsemigroup generated by a single element as the monogenic subsemigroup of the semigroup S, generated by A, and the order of the element A is defined as in group theory as the order of the subsemigroup generated by A. You remember, in group theory, anytime you want to find the order of A, you generate the cyclic subsemigroup generated by that, is the cyclic subgroup generated by that A, and then whatever is the order of the subgroup is the order of the element itself. And likewise here, if you are looking for the order of an element A in the semigroup, you just generate the cyclic subsemigroup by that element, and then whatever is the order, that will be the order of the element. And then a semigroup uh, in which there exists an element that generates the entire semigroup. So look at what we are writing here. S is generated by just A. Then S is called a monogenic semigroup. You compare with the corresponding definition of cyclic group. You see, if a group has one single generator, just like the group of integers, with a single generator, the element 1, it's a cyclic group. So you can now say that the semigroup, if it has one single generator, then it is called a monogenic semigroup. Now, why are we using the term monogenic and not cyclic? You see, in the book of Clifford and Preston, maybe I should mention here that uh, John M. Howie, whose book we are following, was supervised by Preston, and Preston and Clifford, they are the first people to come to write a textbook in 1961 that is entirely on the algebraic theory of semigroups. And then after that, a lot of books were also written. So in their book, Clifford and the Preston, they refer to the subsemigroup, to the semigroup with one generator as cyclic semigroup. But then that terminology actually is not entirely fitted in here. From this theorem, this is why we reveal the structure of the monogenic semigroup. The monogenic semigroup they call a cyclic semigroup, but even though it is not that round enough to merit the description cyclic. In group theory, when you say cyclic group, you see that the group is cyclic. You have a square, a cube, a4, a5, up to an minus 1, and then an will be equal to a. You see, the group will be a single cycle like that. But in the case of semigroup, the semigroup with one single generator is not necessarily very round a cycle that it should be called cyclic actually. In fact, that is why we resort to using the terminology monogenic subsemigroup. In fact, this theorem, theorem 5, is the structure of monogenic semigroup. And then we say let A be an element of a semigroup S, then either all powers of A are distinct, and in that case, the cyclic subsemigroup generated by A will be isomorphic to the group of natural numbers under addition. So it is an infinite cyclic group, or it's an infinite monogenic subsemigroup, or there exists a positive integer. In other words, not all powers are distinct. So there exist positive integers m and r with the following properties: that a to power m is equal to a to power m plus r. It means, the sequence will start a square, a cube, a4 up to am, and then am plus 1. And after you reach am plus r, you are back to am. So which means the sequence will start repeating after some time. And therefore, all uv uh, non-negative natural numbers or non-negative integers, am plus u is equal to am plus v if and only if u and v congruent to each other modulo r. And then also, if you get hold of the set Ka, which is the set of element in between here, from am to am plus r minus 1, am plus 1, am plus 2, am plus r minus 1, and then am plus r will be equal to am. So these are the elements in the cycle. This one now will form a subgroup, a cyclic subgroup of the monogenic subsemigroup. And I think I try to depict the structure here. You start from A1, and then A1 square, A1 cube, A1 raised to power 4, up to A1m minus 1, to A1m, A1m plus 1, A1m plus 2, and then it continues like that, up to A1m plus r minus 1, and then A1m plus r will coincide with A, AM. And from here, the whole thing will start repeating, because am plus r plus 1 will still be equal to am plus 1. And am plus r plus 2 will be am plus 2. And then the entire thing will keep on cycling around here. And so this cycle here is a set Ka, and it is a group now. If you concentrate only on this one, it is a group. It means there is identity among these powers, and also there is the inverses exist here. So you have a cyclic group here, but there is a tail, which means the subsemi group, the monogenic subsemi group, is not just a single cycle, it has a tail. And so therefore the term cyclic semigroup does not fit in there in semigroup theory, because you don't always have a complete cycle like that, like a group. So it always has a tail, a branch like this. And so this is the structure of a monogenic semigroup. But the structure of a cyclic group, we know that it's just a cycle. And so this is justification as to why we are using the term monogenic instead of cyclic. So I just pick, so this is to define the index, the period. You remember in this set, in this theorem, we say there exists an M and an R, such that after you reach A to the M, and then R time afterward, you are back to A to the M. So this A to the M is what we call the index of the element. So every element has an index. M is called the index of the element, and R is called the period of the element. And then this M and R, they are integers. So this is in the situation where the element is of positive order. And we now see that we can define the order of the element to be M plus R minus 1. Because if you count the total number of elements in here, you have in the entire subsemi group generated by A, m plus r minus 1 element. If you do the counting, you can see that there are exactly m plus r minus 1 element in the monogenic subsemi group. So m is called the period, the index, and r is called the period of the element, and also of the subsemi group generated by the element. And then that subgroup contained in the cycle, the subgroup Ka, is called the kernel of the monogenic subsemi group. And then I give you example here. This is just to work with the mappings. If you take an alpha, which is the mapping from the set of 1 to 7 elements. You have 1 is mapped to 2, and 2 is mapped to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 5. This is a map. It is not a permutation because we can see that there is repetition here in the image set. 4 is mapped to 5 and 7 is mapped to 5. So it is not a permutation. But then using the usual composition of mapping, you can find alpha square, alpha cube, alpha 4, alpha 5, alpha 6. But after reaching alpha 7, this equals alpha 4. So if you observe, alpha 7 and alpha 4 are the same. And so therefore, from this onward, alpha 8 will be equal to alpha 5. Alpha 9 will be equal to alpha 6. And alpha 10 will be alpha 4. And then it will keep on cycling around this three element, alpha 4, alpha 5, and alpha 6. So this is, but you have a tail, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, alpha 7, and then alpha 7 is equal to alpha 4, then it starts round now. So it has a kernel, and this is the kernel, alpha 4, alpha 5, alpha 6. So this is just an example to see that truly it is the case that you can have this structure in a semigroup. And the index here is 4 because 4 is the first element to repeat, and the repetition start after 3 steps. So therefore the period is 3. And then if an element A in S has finite index and period, then A has finite order. Well, this is true because if the index and the period are finite, you have a finite order, and the order is given by, we have mentioned this, it is the index of A plus the period of A minus 1. This is actually how you calculate the order. If you get hold of the index and you know what the period is, then add those two and subtract 1, you get the order of the element. And it is clear that for every pair MR of positive integer, there does always exist a semigroup S containing an element A of index M and period R. So give me any positive integers, a pair of integers. I can always construct a semigroup where there is an element I can pick with index M and the period R. And it is not difficult to see that in the semigroup, full transformation semigroup on the set 1, 2, 3 to M plus R. So if you look at the set of all mappings on this set, inside that semigroup, you can pick this map and square it, get all the powers of this mapping. You will see that alpha M will be equal to alpha M plus R, so that the map will have index M and the period R. So, and this mapping is just nicely constructed: 1 to 2, 2 to 3, 3 to 4, and then 4 to 5, M to M plus 1, M plus 1 to M plus 2, like that, up to M plus R minus 1 to M plus R. And then M plus R is mapped to M plus 1. Instead of mapping to M plus R plus 1, it mapped back to M plus R. In fact, it is this construction that we did here. It is the same type of element. You see, this is our M, and our R is after three step after M. So that is it. This is just, we generalize that construction in that example. So which means if you give me any pair M and R, I can always construct an element in a certain semigroup here, Tx, whose index is M and period is R. And this means, and it is also not difficult to see that two monogenic subsemigroup are the same if and only if the generators have the same order. Because if the order of A and the order of B are the same, then the two monogenic semigroup will be isomorphic, and vice versa. And so therefore, we can conclude that given any pair of element MR, one can just speak of the monogenic subsemigroup MNR. So which means corresponding to every pair of integers, positive integers MR, there is exactly one monogenic subsemigroup up to isomorphism. So you can have so many, but they are all isomorphic to each other. So we have exactly one and only one monogenic semigroup corresponding to the index M and the period R. And up to isomorphism. This is always the case. And in fact, this is the notation, this is a standard notation being used in the algebraic theory of semigroup for monogenic subsemigroup generated by element of index M and the period R. And so therefore, the order of the subsemigroup or the order of the semigroup will be M plus R minus 1, as we have seen in the formula over here. And then when you talk of the index 1, it means the first element is the first to repeat. This is nothing but the cyclic group of order R. But that will be 1 plus R minus 1. And then you have a cyclic group. A semigroup is called periodic if all of its elements are of finite order. And a finite semigroup is necessarily periodic, because if you have a finite semigroup, then all elements must be of finite order. So therefore, automatically it is a periodic semigroup. But you can have a semigroup that is not finite but periodic. In other words, the semigroup itself is not finite, but every element in the semigroup is of finite order. So here, theorem 9, we say in a periodic semigroup, every element has a power which is an idempotent, because every element is finite. And so therefore, corresponding to every element A, the cyclic or the monogenic subsemigroup has a kernel, and the kernel is a group. So one member of the kernel, which is a power of A, will act as the identity. And if it is the identity, its square will be equal to itself. So that will be the required idempotent that we are looking for. So therefore, there is always a power of every element in a monogenic semigroup that will be an idempotent. And then, so this is the content of this theorem. Are you with me, Mr. Chairman? Mr. Chairman, sir?
I'm
Yes, we
fully
are
with
with
you.
you.
Okay,
I'm
thank
fully
you.
with you.
I just
We
wanted
are
to
with
confirm
you,
because
sir.
the silence is too much. Okay, then.
You want noise?
Okay. So if the
See,
hypothesis of periodicity is dropped, then we can no longer guarantee the existence of an idempotent. Because if you say, if you try to insist that you want to have an idempotent in every semigroup, that is not necessarily periodic. So if this hypothesis of attaching periodicity to the semigroup is removed, then you can no longer guarantee the existence of idempotent in that semigroup. For example, look at the semigroup of natural numbers with addition. This semigroup has no idempotent because this semigroup means 1 plus 1, and then there is no way you can add a natural number to itself and get the same natural number back. Except if you impose include 0 in the semi, but 0, we assume that 0 is not there here, so the 0 number is not there. So this semigroup contain no idempotent. So it is not the case that you must always have an idempotent in every semigroup, but if you are certain that your semigroup is periodic, then you can be certain of the existence of idempotent in that semigroup. So I think this slide is the end of my discussion for the monogenic semigroup. I can now talk of the ordered sets and semilattice. So this is another phase of discussion now. We want to talk about ordered set and semilattice. These are still basics that we require when we go deep into the theory. So most of these things I'm going to mention now are known to the members, but just in order to clear our memory, to refresh our memory. So I start with the definition of partial order, because I'm talking about ordered sets. So I define partial order. And then a partial order is a binary relation uh, satisfying the three conditions. The first condition is that it should be reflexive. Second condition, it should be anti-symmetric or antisymmetric. And then the third condition should be transitive. This we all know. So if you have a binary relation, we know is a subset of the Cartesian product x cross x that is reflexive. Every element is related to itself. Antisymmetric, that whenever x relate to y and y relate to x, then x and y must to be equal. And then transitive. If x relate to y and y relate to x, then x relate to and y relate to z, then x relate to z directly. This is transitivity. You remember we define equivalence relation by replacing antisymmetry with symmetry here. So here, if you have reflexivity, antisymmetry, and the transitivity, then the relation is a partial order. And most of the time, we just say order relation. We drop the term partial and the order relation. But we will see why we have to say partial order in a moment. And then traditionally, one writes x less than or equal to y for a partial order relation rather than x comma y belong to omega. Instead of saying x and y are omega related, we just say x is less than or equal to y. We use the standard notation of less than or equal to, because this is the usual order relation or partial order relation with respect to numbers. And so most of the time we use that less than or equal to. So, but you should not confuse your mind. It depends on which element you are dealing with, because this element may not necessarily have to be numbers. And if they are not numbers, you cannot think of this as less than or equal to. It is just a relation. We say x is related to y under the relation less than or equal to. So this is a symbol used to denote a partial order relation, just like a standard symbol that we are going to adopt. So we shall follow this convention and also write x is greater than or equal to y to mean what? To mean y is related to x. So if you want to say y is related to x, you say x is greater or equal to y. In other words, y is less than or equal to x. And then x is less than y to mean x is related to x and x is not equal to y. And then x is greater than y with the same meaning. Actually, y is related to x and x is not equal to y. So all the notations, I believe, are very clear. Now, a partial order. Now we resort to using less than or equal to for our partial order. So I will never have to mention omega again. Whenever I want to say partial order, the symbol will be less than or equal to. But with the understanding that I may be dealing with an arbitrary set X that is not necessarily of numbers. So it all depends on the nature of the members of the element to be able to interpret what less than or equal to is. For example, if the set consists of a set of sets, and then less than or equal to here will be containment. A set is contained or subset of another set. So you can see that the depending on the context, the meaning will change or the interpretation will differ. So a partial order is called a total order if it has the extra property of uh, saying, you see, we have three properties for the partial order, but if it is to be a total order, you must have an additional fourth property that for all x and y in x is less than or equal to y, and y is less than or equal to x. In other words, any two members of the set are comparable. So this is to say that any two elements in the set are comparable, because under a partial order, if x is related to y, we say x and y are comparable. So therefore, if given any two elements, they are always comparable.
Please,
Then,
Idris, mute your microphone. Idris, mute your
okay.
microphone, please.
So if they are always
Idris,
comparable, maybe I should. Okay, I think. So we say the partial order is a total order. And so this is the difference. That is why here we have to say partial order, because there is the notion of total order. Total order is when any two elements in the set are comparable, that is, are related by the relation. So, but most of the time we just say order. If we say order relation, we are referring to the partial order. If we want to mean total order, we have to emphasize total here. We have to say total order. So a partially ordered set is now a set X together with a partial order, just like giving the set a structure of the partial order. So this is a structure now. You remember how we define structure? We take a set and then we define something on the set and say the pair is called so. Like we say we have a collection of subsets satisfying some property. We say the pair is a topology. Or we have a set and a binary operation. We say the pair is a group or semigroup, something like that. So here the partial order is like defining a structure on the set. So the pair X together with the partial order, or most of the time if the partial order is understood from the context, we can just drop it and call the set a partially ordered set. And then at times if you read books, you see poset, P-O set, poset, that is partially ordered set. And we write with the appropriate definition, we can also define totally ordered sets, meaning when the partial order is a total order, then X can be called a totally ordered set. Just like the set of natural numbers with the relation of less than or equal to in the numbers is a totally ordered set. Now, if you are in a partially ordered set and you pick a non-empty subset Y of a partially ordered set, then an element A of the subset Y is called minimal, a minimal element if there is no element of Y that is strictly less than A. In other words, if for every element in Y is always less than or Y is less or equal to A, implies A is greater than A is equal to Y. So no element of Y can precede A. This is what we are saying here. Whenever it so happen, then you will discover that the two elements are the same. And if this happen, then you say A is the minimal element of the subset. And then B, an element B is called minimum. This is the notion of minimum. There's difference between minimal and minimum. If B is less than every element, that is for all Y, B is less or equal to Y. So no element of B does not dominate every element. B is always preceding all members of the set. Okay, it cannot dominate every member of the set. So and there is no, these notions are not the same. You may think that the concept of minimal and minimum are the same, but they are not the same. It is evident from the definition that a minimum element is minimal. Minimum is minimal, but you can have minimal that are not minimum. So please, this concept should not be confused. Uh, but it is true that in a partially ordered set, one can perfectly have a minimal element that is not a minimum. So this should be clear. And then the following elementary fact can be easily verified. I did not include the proof because it is clear from the definition. If you have a non-empty subset of a partially ordered set X, then
Hello, sir. We are not seeing the screen.
you are not seeing the
Screen,
screen
sir.
again. Oh,
Yes.
okay. Uh,
Well, me, I'm seeing it here.
I'm seeing it too. So
okay.
good. Maybe there's a problem. I'm seeing the screen.
Okay, sir. Okay, sir.
Okay.
I'm
But
seeing the screen too. I'm seeing the screen too. Maybe that person should log out and come in back.
The screen is clear, yes.
me, I'm not seeing it again after that adjustment. Okay.
He has
And
removed
just
it.
Is it
Yeah,
back
I'm
now?
seeing
Clearing
it
again.
again. Yes, it's
Now he's
back.
back.
Okay. I think he too should see it now.
okay. Please mute your microphone. Mute it, please.
Okay.
Thank you.
So after defining minimal and minimum, we just immediately have this observation that if you have a non-empty subset of a partially ordered set X, then Y has at most one minimum element. You cannot have more than one minimum, because it cannot be true that two different elements are always less than or equal to every other element of the set, because one of them must be less than or equal to the other. Actually, this is clear. If you have two different elements, B and C is less than or equal to B, Y for all Y, and also B is less than or equal to Y for all Y, then it means the two must be the same. The two must, when you compare the two, you must have B is less than or equal to C, and C is less than or equal to B, and that will imply B and C are the same. So therefore, you cannot have more than one minimum element in a set, in a partially ordered set, actually. But for minimal, you can have so many minimal elements. Minimal element can be many. And if Y is totally ordered, then the term minimal and minimum are equivalent. If it is totally ordered, please, members, maybe you should just check this by yourself. Try to convince yourself that the notion of minimal and minimum are equivalent in the situation where the set is totally ordered. That is, the subset itself is totally ordered. Now, we define minimal condition and well-ordered set by saying a partially ordered set is said to satisfy minimal condition if every non-empty subset of X has a minimal element. And a totally ordered set satisfying the minimal condition is called well-ordered. So a set is said to be well-ordered if it is totally ordered and is also satisfy the minimal condition. This is also clear. The corresponding notions of minimal, minimum, and maximal condition are analogous. In fact, the same way you can just analogous definition, just like a kind of dual version of the minimal will give you maximal. The dual version of the maximum will give you maximal, and so on. So this one can come up with the corresponding definition for maximal, maximum, maximal condition, and so on. Here, so this is where we start trying to connect these ideas to semigroup theory. We say if Y is a non-empty set subset of a partially ordered set X, then we define a lower bound. Lower bound as in analysis. This is the same notion actually. We define a lower bound. We say C is a lower bound if C is less than or equal to all members of Y. So it is a lower bound. It's the same thing. Okay. And if the set of all lower bounds is not empty, you see, all lower bound, if the set is not empty and it has a maximum, then the maximum is called the greatest lower bound, the GLB. But in the language of ordered sets theory, we call it meet. We say the meet of Y. So when we say meet of Y, we are referring to the greatest lower bound, the GLB. And then the meet D, in other words, the GLB of a set Y is unique if it exists. You cannot have two different GLBs or meets. And so we can write it as the meet. So this notation is justified because it is unique. Otherwise, if one write this wedge, what is it called? I think this is called wedge of Y, such that Y is in Y. If one write this, and the meat is not unique, you will be confused about which meat are you referring to. But since the meat is unique, we can write it in terms of Y. And so therefore the notation is justified. For example, if Y consists of just two elements A and B, then we can write the meat of A and B to be equal to A wedge B. And so this is actually the notation. And then with this description, we can define lower semilattice. We say a partially ordered set is called a lower semilattice if any two elements from this set have their meets to exist. So that is, there exists the meet for any two elements. So any set of two elements has a greatest lower bound. That is what we are saying. That is, there is the greatest lower bound for any set of two elements. So the meet exists. And then if that is the case, then you call the partially ordered set a lower semilattice. And if we have the stronger property that for every non-empty set, not just set of two elements, but for every non-empty set, the meet exists, then we have a complete lower semilattice. So please, this is just a definition now. Now, in a lower semilattice, we have that for all A and B, because a lower semilattice is a partially ordered set, then you can talk about A less than or equal to B. So we have that A is always less or equal to B if and only if the meat is equal to A. This is just an immediate observation arising from the definition of lower semilattice. And then you can define analogously upper bound, list upper bound, join, and then list upper bound is referred to as join. And then you can also define upper semilattice. You see, we define lower semilattice with respect to the greatest lower bound, but then upper semilattice can be defined with respect to the lower. It's just the dual version of this, and complete upper semilattice. All this can be defined, but for the purpose of our discussion here, only the lower semilattice is sufficient. So if X is a complete lower semilattice, is a lower semilattice or a complete lower semilattice and a complete upper semilattice, then we call it a complete lattice. So a lattice is a partially ordered set that is a lower semilattice and also an upper semilattice, or complete. You can also add the prefix complete or suffix complete. Now, in these circumstances, we may wish to emphasize the lattice structure of a set. And so instead of just saying the set, you have to pronounce that the set has a partial order and it has the operation of the meet and also the operation of the join. So join is denoted by a wage, V, this va, V. And then by a sublattice of X, we shall mean a non-empty subset X of Y, Y of X, such that one that is closed under taking meet and taking join. So if the subset is closed under taking meet and the taking join of any two members coming from the set, then it is a sublattice, something like that. Okay. Now this is the single most important theorem that we are trying to actually discuss here. We say if you have a lower semilattice, so you remember the definition of lower semilattice, it is a partially ordered set in which any two element has a meet. The meet of any two element exists and it is unique. Then, given a lower semilattice, I can define from it, using the meet as a binary operation, I can define a commutative semigroup consisting entirely of idempotent. And this is the way to do the definition, in which the connection between the meet and the partial order is that two element A is less than or equal to B if and only if the meet of A and B equal to A. And then conversely, you see here I started with a lower semilattice and it gave rise to a commutative semigroup of idempotent. Now, if you give me a commutative semigroup of idempotent, then I can define from that commutative semigroup of idempotent a relation less than or equal to an E using the binary operation there, dot, by saying A is less than or equal to B if and only if the product A, B equal to A. And then with respect to this definition, this is a partial order, with respect to which E is now a partially ordered set, and that it is also a lower semilattice. So if you give me a commutative semigroup of idempotent, I can define or I can construct out of it a lower semilattice. And if you give me a lower semilattice, I can construct out of it a commutative semigroup of idempotent. This is kind of telling us that these notions are the same. It means the notion of a semi-commutative semigroup of idempotent and that of a lower semilattice, they are just the same thing. They are equivalent notion. So one can always think of a commutative semigroup of idempotent as a lower semilattice when he needs the partial order in order to progress in his research in the semigroup. Or you can also transfer from the lower semilattice to a commutative semigroup of idempotent whenever you need the binary operation and the idempotent property of the element to make progress in the research. So one should freely think of a lower semilattice as a semigroup of idempotent that is commutative, and also vice versa. I think this is just, actually this entire proof here is just a pronunciation of what I have already said. So it's just we are just saying if you have a lower semi-lattice, then it is not hard to verify that uh, when you define a product with respect to the meat, the product is associative actually, because both of this, if you say A meat of B and meat of C, and then A meat of B, C with the bracket here, all these two are referring to, both of these two are referring to the meat of the set A, B, C. And so therefore they are the same thing. And so you have associativity and the semi-group. So you have a semi-group, and you can easily check that if you take the meat of A with A, it is A. So members of the semigroup are idempotent, and it is the operation of taking the meat is commutative. So you have a commutative semigroup idempotent, and this formula is also easily checked. And when you do the converse, if you start with a commutative semigroup idempotent and you define a an order relation, a partial order relation, or by this rule that A is less than or equal to B, if A B equal to A, then one can easily check that since A square equal to A, this is a reflexive by partial order, and also it is antisymmetric, and you can check that it is transitive, so that it is a partial order, and then the rest also is I think I have explained all there in the statement of the theorem. Now the effect of this last theorem, all this I have explained also, is that the notion of lower semilattice and commutative semigroup idempotent are equivalent notion and interchangeable. And so we shall use the term semilattice with either meaning, making free and frequent transfer between the semigroup and the ordered set point of view. So we can always think of a commutative semigroup idempotent as a semilattice and vice versa. And when dealing with a semilattice or partially ordered set, if you are trying to describe the order set, one can view it particularly using a picture. If the set is finite, one can view it as what is called Hasse diagram. And the Hasse diagram is to actually write the point of the set. You label them A, B, and then you write A below B, that is B to appear above of A if A is less than B or less than or equal to, and there is nothing in between them. So I think this is just what we call Hasse diagram. And this is practically used in theory in trying to describe ordered sets. I think the this is the end of this discussion of today, and thank you for your attention. Time, Mr. Chairman, sir. Ashe ni kaɗai nake ta ihu na tun ɗazu. Abin ya yanke ma tuntuni. Wallahi.